Okay, let's do some calculus. This is section 4.2, Rolle's theorem and the mean value theorem. In this video, I'll just cover Rolle's theorem. And in the previous section, the extreme value theorem states that a continuous function on a closed interval from a to b must have both a min and a max on the interval. Both of these values, however, can occur at the endpoints. Rolle's theorem gives conditions that guarantee the existence of an extreme value on the interior of that interval. Now notice it doesn't guarantee both a min and a max on the interior. It just says there might be one or the other. A min or a max. Somewhere in the interior, not on the endpoints. So Rolle's theorem here, set theorem 3.3, let f be continuous on a closed interval ab. So we have to have a continuous function on a closed interval. And it differentiable on the open interval from a to b. So in between those endpoints it has to be differentiable. If, now here is the given condition, if f of a is equal to f of b, then there is at least one number, c, in the interval from a to b, such that the derivative will equal 0. Now what does this pre-existing condition really mean here? F of a equals f of b. Well, if we look down here in the graph, here are our endpoints, a and b. And if we plug a into the function, it gets mapped up to the graph, and then when we hit the graph, we get over to the y-axis. So this height here that they're calling d, we could also call f of a. We put a into the function, out comes f of a. Over here is point b. If we plug b into the function, we map it up to the graph, and then we go over to the y-axis. So f of b is also at this height. So f of a is equal to f of b. Graphically, the endpoints of the interval that we're looking at have to be the same height on the y-axis. And then the theorem goes on to state that if we have this condition met, then there has to be at least one number c in between a and b, such that its derivative equals 0. And remember, when the derivative is equal to 0, we have a horizontal tangent line. And in the previous section, you know, that could be a min or a max. And let's see what's going on here in this graph. F of a and f of b are at the same height. And we have a continuous function. But we see it's not differentiable. We have this sharp peak. So this function at this point is not differentiable. So there is no place where that derivative might equal 0. So we had f of a is equal to f of b. We were continuous, but we weren't differentiable. So we will not be able to find a place where the derivative is equal to 0. Okay, example 1, illustrating Rolle's theorem. First it says find the two x-intercepts of this function, and then show that there is a derivative equal to 0 at some point between those x-intercepts. So graphically, what we want to do is find two intercepts. This is x squared. It's a parabola opening upward. So we know it's going to look something like this, and we assume it's going to cross the x-axis in a couple places. So let's find those interesting points by taking our function and setting it equal to 0. So f of x is x squared minus 3x plus 2. And we're going to set that equal to 0 to find our x-intercepts. Well, over here we have a polynomial that we can factor. The factors of x squared are x and x. The factors of 2 that add up to -3 are -2 and -1. And now that we've factored it, set each factor equal to 0. X minus 2 equals 0 means x is equal to 2. X minus 1 equals 0 means x is equal to 1. So there are the two x-intercepts. We know that x is 2 and x is 1. And what we've done is, again, graphically set up that precondition of Rolle's theorem. So we had these two endpoints. This is +1, this is +2. When we think about Rolle's theorem, we need f of a equal to f of b. Well, if we look over here to the y-axis, both of these intercepts are going to get mapped over here to y is equal to 0. So this takes care of the precondition f of a equals f of b. Rolle's theorem says that in between these points, there is a point with the derivative equal to 0. So we are going to take our original function, and we're going to take its derivative, f prime of x. So we have a 2x minus 3. Now we set the derivative equal to 0. 2x minus 3 equals 0. So we add 3 to both sides and divide by 2. X equals 3 halves. So at x equals 3 halves, we do have a horizontal tangent line, or a derivative equal to 0, and that point does fall in between 1 and 2. And a more exact graph is right here. We found the x-intercepts at 1 and 2, so that met the condition f of a is equal to f of b. And we know that somewhere in between there, we're going to have a derivative equal to 0, and therefore a horizontal tangent line. Rolle's theorem states that if function f satisfies the conditions, then there must be at least one point between a and b with a derivative equal to 0. There may, of course, be more than one such point. So here is our given function. It says find all values of c in this interval from -2 to 2 such that f prime of c is equal to 0. Now we're not sure if we can even apply Rolle's theorem. We have to make sure the endpoints are at the same height. So here is our function. We're going to plug in the endpoints 2 and -2. F of 2 is going to be 2 to the 4th minus 2 times 2 squared. 2 to the 4th is 16. 2 squared is 4 times this 2 is 8. 16 minus 8 is 8. Now if we check the other endpoint, f of -2. We're going to have -2 to the 4th power minus 2 times -2 squared. Well, -2 to the 4th is the same as 2 to the 4th. The even exponent will take care of any negative sign. So that is also 16. -2 squared is 4 times that 2 out front is a minus 8. 16 minus 8 is also 8. So f of a is equal to f of b. The initial condition of Rolle's theorem has been met. So now we know that somewhere in between 2 and -2, there's at least one point with a derivative equal to 0. So here is our function. Let's take its derivative. F prime of x is going to be 4x to the 3rd minus 4x. We take the derivative and set that equal to 0. Now let's factor some stuff out. It looks like we can pull a 4x out of each term. So we're going to be left with an x squared minus 1 in the parentheses. X squared minus 1 is a difference of squares. So we can break that further down into x minus 1 times x plus 1 equal to 0. And now we have 3 factors. Set each factor to 0. 4x equals 0 means x itself is 0. X minus 1 equals 0 means x is positive 1. X plus 1 equals 0 means x is negative 1. So there are 3 points where we have horizontal tangent lines. Rolle's theorem guarantees at least one. And for example 2, here's the graph to go with it. The first thing we did was check the endpoints. F of -2 was 8. F of 2 was also 8. So we know we can apply Rolle's theorem. We took the derivative, set the derivative equal to 0 to find the horizontal tangent lines. That occurred at -1, at 0, and at positive 1. Be careful when using a calculator. Technology pitfall. A graphing utility can be used to indicate whether the points in the graphs in example 1 and 2 are relative minima or relative maxima of the functions. When using the graphing utility, however, you should keep in mind that it can give misleading pictures of graphs. For example, if we use our graphing utility to graph this, with most viewing windows, it appears that the function has a max at x is 1. It looks like we have a parabola opening down, and it looks like we're going to have a max right there at the top of that hill. However, you can see that f of 1 is 0. You know, if we plug x is 1 in here, we're going to have in these parentheses, 1 minus 1 squared is 0 squared or 0. So we're going to have 1 minus 0. And if we plug that f or 1 in here, we're going to get 1 minus 1 is 0, times 1,000 is 0, to the 1/7 power is still 0. So we're going to wipe this out, and we're just going to be left with 1 divided by 1, which is 1 minus 1. 1 minus 0 minus 1 is 0. So the graph is misleading. There's a hole in the graph, and the value at x is 1 is actually down here.